So our next speaker is Mandy Cheung from Kavli IPMU, and she will tell us about cluster structures for the infinity singularity. So please go ahead.
Yeah, thank you very much for the invitation, and thank you to all the organizers for organizing this conference. And again, thank you very much for inviting me. And today I'll talk about the cluster structure for the A infinity singularity. And that is a joint work with Jenny August, Eleonore Faber, Sira Gratz, and Sibylle Schroll. And then we are also, this is also the second paper of our collaboration as well, in synchronized with the first talk. So before we start, before we talk about the infinity case, let us go back and recap the cluster structure of Grassmannian 2n, which like we consider in general an n+3-gon, but let us now, for example, take a look at the 5-gon with a triangulation. And then this whole thing will give us a set where we have the cluster variable labeled by the edges. And then the exchange relation can be described by flipping the triangulation like this. Like we flip like this edge with, maybe I should use another color. This edge with this edge. And then that gives us the exchange relation by here we flip the original variable x1 3 and then x2 4, and then we have the right hand side be labeled by the side of the 4-gon, and then here we can see we obtain a cluster structure. And then as illustration, there's like two observations as illustrated here, like in a triangulation that we have all the diagonal doesn't cross, and then when we flip, then it cross, and then that gives us the mutation. And because we only have 10 minutes, so this one is actually giving us the Fourier relation for Grassmannian 2n, and in general we can consider the n+3-gon, and then that gives the Grassmannian cluster structure for GRO 2n, which is type n+3, which is of type an. And then Jensen-King-Su introduced a additive categorification for cluster structure. Actually, their construction is more general, is for Grassmannian Kn. So that what they have is the indecomposable object in the category will correspond to the cluster variable in AKN. And then the cluster tilting subcategory will give us a set or a cluster in the algebra. And their construction is they consider the ring, which is defined by 6y quotient xk minus yn minus k. And then they have this group action by the group of unity adding on the ring this way. And then they define the Grassmannian cluster category as the Maximal-Macaulay module with this action. So what to think about A infinity category, what we want to think of is to push n goes to infinity to the work of Jensen-King-Su. So because today here we'll focus only on the type A case, so we are thinking GRO 2n, Grassmannian 2n. So this is the ring that we have. To have n equals to infinity, we can imagine that we kind of have like this yn minus 2 go away. And then this is the ring that we are going to consider. And then we similarly consider the Maximal-Macaulay module with set graded. And this is actually the curved singularity of type A infinity. And then here we have, then we want to look at the object in this category, which either this form or ideal generate coming from xy to the k shift by the j1. And then the next thing, we begin by looking at n+3-gon. So we want to give a combinatoric model of this category, which we can imagine. Again, we have the n+3-gon. Like, think about, we have all the edges goes to infinity, that we kind of have this with with set method. So this is what we have. We should have a this with the discrete map points labeled by set, and then we compare it by with the point infinity. And then we have the art in this gon is either something like this or a art that join the infinity, which we call finite art and infinite art. And then again, we begin by thinking about the triangulation of n+3-gon. So we can similarly think about the triangulation of this computed infinity-gon, which, as we might have imagined, is the maximal set of non-constant art of this infinity-gon. And then there's two notations that we have. We'll call the triangulation as locally finite if for all the map on, there's only finitely many arts in the triangulation with n point A, but we can also have art that infinitely art with n point A, which we call something a right phantom, or similarly a right phantom, left phantom, which is we consider the set you can see here with the n point on A, but we go on the right with infinitely many endpoints, and then this is something what we call the right phantom. And then Hong-Jorgensen shows that for infinity-gon, every triangulation is either locally finite or contain both left and right phantom. And then the work of Bauer and Sira Gratz show that the triangulation of the computed infinity-gon will be one of the following. And you can see here, this one is locally finite. We have right phantom here, left phantom, and then something like that. And this is the triangulation we can have for completely infinity-gon. And then we look at with Jenny August, Eleonore Faber, Sira Gratz, and Sibylle Schroll. Then we look at the extension group and the home group, because that is what we want to have for the constituting. And then we show that with another work as well, that when the art calls, then we have the extension group is non-zero, which is isomorphic to C, which those are some cases are like that. But then if they don't cause, then we have the extension group as 0, which can be illustrated like that. Okay, here are the what we have for the extension group. Okay, I'll look at the time. And then similarly, we can have the calculation for the home group, which this is something that we can have. And then once we have that, we can look at the mutation. There are two types of mutation. First, we can look at the picture here first, which is similarly to what we have for the Grassmannian 2n when we flip the diagonal, or here, those are for the finite art. And you can see this is what we can have for the infinite art. And then what we have is we consider a maximal or more rigid subcategory. We can talk about the definition afterward, corresponding to a triangulation of the computed infinity-gon. Then we'll say we will have the indecomposable object in the subcategory is mutable if and only if the corresponding art here is mutable, something like that. And then furthermore, we have the left and right mutation coincide and correspond to what we think as a mutation. And then actually type A infinity cluster category have been studied by many others. And so at the end, I will wrap up by, okay.
remind you that it's not so much time, but take your time to wrap up.
This is the final slide, and you can see I didn't cut it out. First, what we have is we have a very lateral subcategory of our category. We cover the Holm-Jefferson A infinity category. And Fisher study completed the Holm-Jefferson category under homotopical limit, and then he obtained this D-bar triangulated subcategory. And we also have Picard-Ullmann's category, which is built on includes a total of category. And they also, what they have is they have the indecomposable object corresponding to the starting and ending at the accumulation point. And here their category will denote in this way. And then what we have is we can show that our stable category, the stable category, stable category of our Gauss-Manin category is equivalent to the Picard-Ullmann and the Fisher's category. And that is the end of my talk. Thank you very much.